This is actually, if I had to choose one place in the world that I think would be most interested in, and appropriate for hearing about my research, I think this would be the place. There are a lot of people here who have been active in CSCL and are interested in it, more so than I could think of in most other places in the world. So, as Annika said, I've been working on this research project called Virtual Math Teams for the last dozen years. It's quite a complicated project, and there's a lot of things, a lot of different aspects that I could discuss. It became so complicated that I didn't feel that I could present it coherently in a single paper at a conference or in a journal or a single talk. And so I decided to write a book about, actually my third book about it, which it just came out. And so what I'd like to do is summarize what I said in this book in my talk today, and actually in the 3 talks this week. So today I'm going to talk about design of an online environment for kids to learn and work in dynamic geometry. And over here I have captured the environment, and I'll just play sort of in the background, so when you get tired of paying attention to my slides, you can look over and see what the 3 students are doing here as they're chatting and manipulating geometric objects. So I'll start that up. This is what we call the VMT replayer, and it's replaying an actual session by 3 students and replaying it at double speed. So it'll go along a little faster. And you can see what dynamic geometry, how dynamic that is when the students get a hold of it and start playing with it. So I have 3 talks. Today is about the design of the technical environment, the software and the supports we have for researchers and as well as for the students and teachers. Tomorrow I'm talking about the didactics, so the curriculum. So this is right here is a piece of curriculum that they're working on, some instructions and a geometric figure for them to play with and analyze. So that'll be, tomorrow will be the didactics, different parts of the curriculum. And then the following day on analysis, so how we analyze what they're doing in a data session. So this is a summary, the 11 chapters of the book, and also the 11 parts of today's talk. So these are different dimensions that I think about in terms of the design project, or the project taken as a design. So the first one, sort of an overview. This is how I characterize the research question of our research project. So how should one translate the classic education approach of Euclid's geometry into the contemporary vernacular of social networking, computer visualization, and discourse-centered pedagogy? So we want to take, obviously, Euclidean geometry is something that's been around for thousands of years. People have been studying it in different ways. And look at how it's been studied, how that's changed, and how it should be, perhaps, for the future, to make a more exciting topic for students to learn about. And looking at this research project as multi-dimensional and as a design-based research project, which means that it evolves over time constantly. And so I visualized this research agenda in terms of this graphic. So translation is a geometric term. You translate something by moving it from one point to another. This is a point in history, a couple thousand years ago, 300 years BC. when Euclid worked on a clay tablet to the future when students work on a digital tablet. And as an example of how fast the field is changing, when I made this graphic up here to include in my book, I had to Photoshop it because you couldn't actually do dynamic geometry on an iPad back in March. So I Photoshopped it onto there. But this image here I took for the lecture today, actually on my iPad. So in the 6 months since March, the technology has changed pretty radically, actually, from having to do dynamic geometry on a laptop to being able to do it on an iPad, which may make a big difference to students. So things have been changing now for over 2,000 years, and they're still radically changing from day to day. So if you look at the history of geometry, the early Greeks started to invent geometry back in the golden age of Greece. And it's quite interesting to see how they used diagrams and a specialized text. This was the first alphabet-based language, was Greek back then. And they developed a special vocabulary for doing their geometry, a vocabulary that we still use today. And they had a small distributed community around the Aegean area. And so what I'm trying to do now is create a technology that will allow students to do something similar, to have persistent diagrams like that, and to work in distributed communities online using the web to invent their own geometry, their own understanding of geometry. And so that they learn this small vocabulary of geometry, and they learn how to manipulate and construct geometric objects themselves. Then several hundred years after the beginnings of geometry, Euclid came along, also in Greece, and systematized the theorems of geometry. And I argue in my book that that led to a kind of bureaucratization of the process of geometry, which had been a very creative, human-centered community approach. It also had a very positive effect. Namely, his approach developed this deductive argumentation, which became really important for all of Western science, a way of thinking rationally. And geometry has always been appreciated in Western society as a way of training students to think rationally, to make deductive arguments and so on. So that's a very positive thing without which Western science might not have been possible. But it also had this negative thing that it kind of bureaucratized things. And it projected, as Plato argued already, Plato lived just before Euclid. They may have actually known each other, or at least Euclid probably studied in Plato's academy. And Plato, as you know, thought about a world of ideal objects or ideas as separate from the world that we live in, the physical world. And this was a projection based largely on mathematics and geometry, thinking of it as otherworldly things instead of thinking it as creations by students working together. The other thing is that it became something that was thought of as individual thinking rather than a community of thinkers. So geometry was created by a community of thinkers in ancient Greece, but then it became something that individual students were trained to do in their heads rather than as a community process. And so here we're trying to get back to a community process of doing geometry. And so then by the 18th or 19th century, it became even more formalized into formal logic and axiomatic systems. But now we have, in the last 10 or 20 years, we have a new a new development, namely dynamic geometry. And that's where you see that you can move things around and change the scale of things very easily. And that's part of the geometry. So it's a new form of geometry. So geometry has actually, even though it seems like geometry hasn't really changed since it was invented by the ancient Greece, it has gone through quite an interesting history. And we're trying to push that history further to get around some of the problems that have come up in the middle. So I try to work out some philosophic aspects of this, both critiquing the approach that Plato introduced into the history of ideas and the history of geometry in particular, and get back to geometry as a social construction. And I think that dynamic geometry has the potential to help here and to provide something to students that maybe where they can grasp some of the potential of seeing what they're learning as a social construction that they're involved in actively. And so they're creating geometric objects. They're not just repeating things that are taken out of Euclid's book. And so they start to see themselves as active agents in the social nature of geometry as a product of community discourse. And as I started to explore dynamic geometry, I started more and more to focus on this notion of dependency. Dependency is something that's not been discussed much, even in the recent research on dynamic geometry. But I think it's really at the core, at least at the core of what I want students to get out of it. I want them to be able to understand this notion that some things are designed to be dependent upon other things. And therefore that proof, which has always been an important part of geometry and became an even more and more important part of geometry as geometry became axiomatized, that the proof isn't something that you get from some authority like Euclid, but it's something that comes out of the dependencies that are designed into geometric figures, like the figure that we saw over there, which has now zoomed off the screen. And that students can, as part of learning how to do this dynamic geometry, they can become designers of dynamic geometry figures that have certain dependencies built into them. So they can start to look and understand geometry as a design field, a field of design, where they learn to design geometric constructions and the design that they want to do is to build in certain dependencies. And then these dependencies will sort of automatically lead them to understand the proof. A lot of students who study geometry now don't really understand proof. They're bothered by it. It's something they feel is beyond them. They can't get a hold of it. They can't really understand what it's all about. But if they understand that they've designed these figures to have certain dependencies that they want into it, then that pretty much gives them the core notions of proof. And that's why I think dependency is an important concept. And I wanted to design the environment and the curriculum to bring out that notion of dependency for the students. So here's an example. Here we have two line segments, a line segment AB and one CD that cross each other. And so if you construct this in a dynamic geometry environment, software environment, and you place a point E at the intersection of these two lines, then no matter how you move these points and lines, point E will always remain at the intersection of those two segments. So its position, the position of point E, is completely dependent upon the positions of the two line segments. Whereas if you place a point here at point F along segment AB, it can move, you can drag point F up and down. It has to stay on point AB, on line AB, but it can be anywhere along there. So in dynamic geometry, you can take a point like A and drag it anywhere you want. You can take a point like point F, and it's restricted or confined to being on that line segment. You can drag it anywhere as long as it stays on that line segment. But point E, you cannot drag at all because it's dependent upon being at the intersection of those two segments. So you have 3 points that seem like, in general, points are all the same. A point is just a location on the surface. But they're different in terms of their dependencies. Point A is completely free to be dragged anywhere. Point F is constrained to be on that line segment. And point E is completely dependent upon the other points and can't be dragged anywhere directly. You can move it by dragging the line segments and so on. So here's a simple example of different kinds of dependencies. And here's a little curriculum to step the students through constructing something like this. And then noticing and discussing in the chat among themselves collaboratively these features of the points. And then later in the curriculum, you can come and use those things about dependencies that these lines are made to be only a certain length, but you can move them around. And you can prove the different theorems about congruency. So you can prove that if you have 3 line segments that are fixed in length but can be and are attached like this, you can move point C and point D until they coincide and form a triangle. But there's only one way to do that. In other words, you have to move C over and D over a little bit, and then you get a certain triangle with certain angles in it. And that's fixed. You can only do that one way. You can only make a triangle. Given 3 lengths of the sides, there's only one triangle that can be made with that, which has certain angles in it. For instance, if the lengths are 3, 4, and 5, you end up with a right triangle down here. Triangle E has to be a right triangle. So by understanding the dependencies that you've built into here, you can then make certain proofs that are fundamental to basic geometry. Everyone who studies geometry studies the basic theorems of congruency that that if you're given 3 lengths, then any triangle with those 3 lengths is congruent to each other. They're all basically the same triangle. So now I want to move from this basic idea of dynamic geometry to the technology. So in the 1990s, there were a number of software systems like Geometer, Sketchpad, and Cabri. Have any of you used or seen Geometer, Sketchpad? Okay, just a couple. And these created this potential that I see for students having a radically different experience learning geometry than learning it from a textbook. Here they can actually create their own, move them around, and understand, get a feel for the things like the dependencies of objects on each other. And then more recently, in the last several years, a new version has come out called GeoGebra, which is available for free. And so it's become very popular around the world, really, for use by math students. And it also includes other forms of math in addition to geometry. So once students use it learning geometry, they can also use it for future courses in algebra and calculus and so on. Now, what we've done in the VMT project is to incorporate that GeoGebra technology inside of a collaboration environment. So all of these dynamic geometry systems were made for single users, for a single student on their own computer to manipulate things. And we believe in collaborative learning supported by computers. And so we have a collaboration environment, and we converted the dynamic geometry of GeoGebra into a multi-user system and incorporated it in our collaboration environment. So what you saw here with the two triangles, that was created in GeoGebra, but within this larger environment, which allows students to chat with each other, and where multiple students can look at and manipulate the same geometric figure. And they can also have multiple tabs with different geometric curriculum units in it. So I'm going to describe the technology in the next several slides. So it's called Virtual Math Teams Technology, online environment, and combines the dynamic geometry. And here's a screenshot of it, similar to what was over there. And so you can see it has multiple tabs, so we can have multiple units about curriculum units, and the students can move through them sequentially. It has the chat, a typical chat interface where they type in and it comes up. And in addition, you can point from a chat posting either to another chat posting or to an object in the GeoGebra screen. So you can make deictic references to things. You can say, look at that circle and watch what I'm going to do with that. It has a control button, so students alternate having control of the GeoGebra. So they're not, even though it's multi-user, we didn't want several students manipulating the same figure at the same time. We want them to watch what each other's doing. So one student takes control, and they negotiate who's going to be in control in the chat. They take control, and then everybody else watches what they do, and then they'll switch. So those are the main features of the system. And because it's multi-user, so that means that the students could be anywhere in the world. So we could have in theory, you could have a student in Sweden and a student in the US and a student in China working together in the room, in the chat room. And they would see what each other's doing. And here's a little video that illustrates that. So here's the screens of two students, and here's a list of the students that's listed up there. So here, one student is constructing this line, and it shows up also on the other student's screen. As soon as they complete construction of the circle, then it shows up on the other screen. Now they're going to, I think, switch. Let me try, that person says. And this one says OK in the chat. And so this one's taking control now and is going to create another circle. and it looks like they're going to create a point, dependent point at the intersection of the two circles, and maybe they're going to create a perpendicular bisector between those two intersections. And so everything shows up over here. Now this one is changing some of the color, which shows up red on both screens. And then this one says, let's check. So they're going to check to make sure that dynamically this still remains a perpendicular bisector. So here it created the angle here, and it shows that it's a 90-degree right angle. So this person says it looks good. And now this person is, I think, going to do the drag test. So they're dragging it around to see that it retains its 90-degree angle there, and the other student's screen shows the same thing. Now this one's testing it, dragging it around. Okay, so they conclude that it checks out. Another feature we have is a history tracker, so they can go back and look at the history of their whole session. So along here is the history slider. So the student is sliding the history back to the beginning when they had an empty screen, and now going back through the history and seeing how they built up that construction. And you can see that the other person was not affected by what went on here, but the other person can do the same thing. So they can both look back at the history of what went on in their session at any time without affecting the work that goes on. And this is just showing that this person can be doing some new work now, and it doesn't affect the history, but when you come back to the present, then it shows up there. So we have a number of other tools built into the system to support collaboration, and also some tools for analysis. So the records are persistent, so at any time students can go back in their old chat room and see what they did. They can go through the history and review what they did, and maybe take some screenshots to put into a report, something like that. The teacher can go back and see what that group of students did. If you imagine using this in the classroom where you have half a dozen or more groups of students working, the teacher can't follow what everyone's doing while they're doing it. Or if they're working after school at home, from home on this collaboration, the teacher's not there. So now the teacher can go back into those rooms and see what went on. We also have a session replayer. That's what I had going here, was the replayer. So it shows the whole session, exactly how it happened, in great detail, so the teacher can go through that, or a researcher can go through it step by step, and that's how I do my analysis. And that's what we'll be using in 2 days at the data session, is looking at that. It's basically the same as a video recording, except that it's automatic, and you don't have to worry about adjusting the camera or anything. It captures exactly what the students saw, and everything gets replayed in the way that it originally happened. And then I have here a video showing the replayer, but you saw it over there. So, and then we have some additional features built in for analysis. Log files in spreadsheets that everybody can download. The students can download it. If they want a list of their chat, the teacher can download it to see what went on in the chat, and researchers can download it. And it's very detailed, so it includes GeoGebra actions like this person added points A, B, C, and so on. Or circles. It includes the chat. It includes that people came into the room and left the room, and that they switched from one tab to another. So it basically captures in a spreadsheet version a lot of the detail of what went on. And then you can filter it as a spreadsheet. You can filter out to just see the chat, which is what I usually do to get logs to put into publications and so on. Or you can filter it to look at all the GeoGebra actions to see how they actually constructed something, and so on. And the system is publicly available, it's open source, and so on. And anybody can set up their own rooms, and here's the interface for creating a new room or a set of rooms. There's just a little form that you fill out, giving the name of the rooms, how many copies of the same room you want, and what your project is. Each teacher might have a different project, so all of the teachers' classes have chat rooms in that project, and they can find them easily. And then you can define the different tabs that you want to have multiple chat tabs with different content in them. So we tried to support collaboration with this technology. In addition to the technology, we've developed the curriculum, which I'll be discussing in more detail tomorrow. And we test it, and that's part of the design-based research approach, is that we're always testing and revising in iterative cycles. And so students manipulate the figures in geometry. They talk about the dependency, so the curriculum guides them to talk at each stage about how things are dependent and what that means and how to construct geometry with those dependencies. And then we have teacher training. So we take math teachers who want to use this system, and we have a teacher professional development course, which we have a course running right now for 10 weeks, where the teachers work in groups, just like their students will, using pretty much the same curriculum. And they have these online sessions where they have a problem like the one that you saw over there, of if you have one triangle inscribed inside of another one, what are the dependencies that keep it that way as you drag the big triangle around that keep the small triangle inscribed in it? And it turns out both triangles are equilateral, so they're constrained to be equilateral. How would you do that? How would you construct that figure? And what they do is they drag things around and they try to see what dependencies are active, what are the restrictions on what points can move how. And then they think about how you would reconstruct that, and they try to make the same figure that works the same way dynamically. So this is a group of students, and here's Emily is one of the teachers who's doing it. It's a group of teachers doing this exercise. And then Emily is a teacher, and she has the students do the same exercise after this is a pretty advanced one. They have to learn the basics of GeoGebra first and of using the VMT system, but when they're pretty advanced, they can work on this. So in the data session in 2 days, the data we'll be looking at is data from Emily's students doing this curriculum piece, this curriculum exercise. I don't know if you can read this from back there, but here the group of teachers is talking about their experience. They're reflecting on this experience, and one of them says, "I laughed thinking how hard it was to create an equilateral triangle the first time. We're much better with GeoGebra now." Emily says, "CG and BU are dependent on AD because we use the compass tool to keep the same radii." So this harps back all the way to Euclid's first proposition about how to build an equilateral triangle using circles with the same radius. And that was his proof that this construction produces an equilateral triangle. Here they're using exactly the same argument, just very informally, about how they've created their figure, but using really Euclid's argument from a couple thousand years ago. So it still applies to the dynamic geometry, but here they get a much more tangible sense of how it applies and how they've built it into their diagram and how they did it technically using the GeoGebra and how well how beneficial it was to work as a group. I'm quite sure that none of these teachers could have solved the problem of creating that inscribed triangle on their own, at least not within the hour that they worked on it. But as a group, they did accomplish it. And they realize that not only they learned to use GeoGebra and its tools, and they learned to manipulate dynamic geometry, and they learned to collaborate online in the VMT system. But they did all that because they were doing it collaboratively as a group and discussing it. And here they're recognizing this here. And they're all agreeing. They're saying, yes, so true, and so on. LOL. For me too. So that's kind of a nice reflection by the teachers about it. And the students have similar reflections. So here's the students. So the next task after they do the inscribed triangles is to do inscribed squares. So it's fairly similar, but when the students work on this, and here they are just at the point where they're making the big breakthrough in creating it. They had all of their exercises until this one had to do with triangles, so they hadn't done anything about squares. So they learned how to create an equilateral triangle using Euclid's old method. But then they had a lot of trouble creating a square, constructing a square. But they finally did it as a group. And as soon as they constructed the outside square, then they knew how to do the inside square as a generalization of how they did the inscribed triangles. So this showed to me that they had really mastered what they were supposed to learn from the inscribed triangles, and were able to generalize from that to the inscribed squares. And they all understood it right away, and were able to share that in their chat, that they all understood that. So we can, as analysts, we can look at this chat data and see how a group of students collaboratively learned different things about geometry. And we can document how the fact that all 3 students had mastered a certain conception in a previous lesson by seeing how they apply it in this later lesson. And so that's part of our research on the learning process. So if you think about educational research, how do you know that students learn something in geometry class? Well, if they're all sitting there, like you are, I have no idea what you're learning from my talk. No idea at all, Most of you are still awake, so hopefully you're learning something. But I have no idea what's going on in your heads, right? So I could have given you a test before you came in and give you a test when you leave and see if there's some change in it. But that's about the only way I have to figure out something called learning taking place. But here I have a lot of evidence about what they know, what they can express in their chat, what they can articulate in words, and ask each other and respond. So I have a lot of evidence to see what the learning process was. And like I showed you, I could tell when they worked on the inscribed squares, I could tell what they had learned in the inscribed triangles. Not just because they said things that I understand this or I understand that, but also because they put that knowledge to work in actually constructing something that really worked, and they all agreed on it. And they were all part of that process of constructing the squares. So you can tell there's evidence in that data that they all had learned something that they brought over. And in 2 days, we're going to look at the data across across the 8 hours that they worked on, and we'll see in the beginning sessions how little they knew, even about collaboration or what they were supposed to do in this environment. And as the days went on that they worked in this environment and worked with GeoGebra, you see how much more competent they are to do things. And this example of the inscribed squares is quite difficult. When I first came across the problem of inscribed triangles, it took me several days to figure this out. And I've been doing math for a long time. It took me several days to figure out. And for a group of teachers or a group of students in 1 hour to figure this out was quite impressive to me. And not only they didn't sort of stumble upon it, they didn't look up the answer in Google or anything. They figured it out. It took them quite a bit of struggling and exploration, but they figured it out and they understood what they had figured out, which is kind of the amazing part. So then once we do the research and see the learning processes going on, then we try to develop theory about it or modify the theories that we brought to the project. And so one part of the theory is to try to develop an alternative to the individualistic way of thinking. So when I said I don't know what each of you is learning, that's thinking of you as individuals. So what's going on for you individually in your head, that's different from what's going on collaboratively for this group of 3 teachers or 3 students. And so looking at learning as a collaborative process, looking at collaborative learning as something that's visible in discourse and in action, something that I call group cognition, as opposed to always trying to research individual cognition. And looking at geometry as not something that happens in another world of ideal objects that we have to look up in Euclid's text, but rather as an accomplishment of a community of students constructing things actively and collaboratively. And how do you put together the individual cognition that's going on, the group cognition, and the community cognition? How do those interrelate to each other is quite a complicated and not very well understood part of the theory. And so I've tried to, this is just sort of a diagram with these different cognitive areas and how interaction in the small group is the centerpiece that mediates between these. It's not really an answer, it's more posing the question of how does all this happen? So these are the areas that my research has been focused on recently. Group cognition going back a while. In the last year, I've been focused on theory of resources as mediating the learning going on the different levels, and how the different levels, how there's a unity between them, how they're connected, and how dynamic geometry, learning analysis of that, can be used to help refine these theories. And the idea of resources leads into the curriculum as a set of resources that guides the student learning. So I've developed a whole workbook of about 100 different curricular resources that take students through the basics of dynamic geometry learning in, say, a 10-week session. And tomorrow I'll focus on this pedagogical aspect of and there are different things that I feel are important. First, the hands-on part of dynamic geometry, where the students are actually constructing things themselves in the group. So it's not focused on accepting facts from an authority, but of creating them yourselves. Also, I'm trying to argue against the way GeoGebra is usually used in classrooms. It's used widely around the world, but it's usually used without the emphasis on dependencies, or even necessarily having the students do the work themselves. Rather, it's used as an illustration by the teachers. And so to get around this, I focus on the group doing their own constructions and even creating custom tools for themselves to do further work, and emphasizing this role of dependencies. So the curriculum goes through, there's beginning topics that cover the basic ideas in geometry, in dynamic geometry. Here's an example very quickly of how if you drag this, then all the lengths change, but certain dependencies remain that were constructed into it. Then there's a set of intermediate topics that go through more advanced topics in geometry, like transformations. And here's some examples of that, including stepping them through to create custom tools. And then there are advanced topics, mainly for the teachers more than for the young students, that have open-ended problems, like simulating a factory workflow or transformational geometry. So to summarize, our project is a design-based research project of human-centered geometry. So design-based research is, like I said, an iterative process where we try out different curricular topics with different audiences. We see what happens, we analyze the results, and then we modify the curriculum. And we try to understand what's going on in how they use that curriculum. And I think I will stop there so we have time for some interaction. So I have presented, during the project, I have written up these 3 books that cover the project. This is the sort of the background on group cognition. This is a group of essays analyzing back in 2009, analyzing the results we had at that point. And this covers the current state of the project. And if you want more information, these slides are available as well as the other things. So let me just open it up now, and hopefully we have, I think, over half an hour, plenty of time for a discussion.